This is Jared Johnson, HPC Systems Management Architect at Lenovo. This video is going to be introducing Confluent, a software for managing consoles and hardware. We intend this to be used either in conjunction with XCAT or as a standalone installation. This video is going to be focusing on the case of a standalone installation. So what we've done so far is installed Confluent from RPM in this case, and we've started the service. And we've also created a PAM configuration file to enable the optional PAM integration. Um, so with this configuration in place, Confluent will use PAM to verify passwords. So PAM has the ability to verify passwords, and also if you want to use PAM to also block people from being able to access, you can do that in addition to Confluent's baked-in facilities. But Confluent's baked-in facilities will be required to also pass the user. As a consequence, if I try to run Confetti right now as this user, it's going to be denied access and it's going to fall back to prompting for a name and password, which can be passed in by environment variables if desired. But in this particular configuration, out of the box, no username and password will let the jjohnson2 user in. But the root user can connect. So what the Confluent service does is it listens on 3 sockets: a Unix domain socket, a TLS network socket, and an HTTP socket. The Unix and TLS socket speak the same protocol. HTTP presents the same data, just framed with HTTP protocol rather than the Confluent protocol. Uh, when connecting to the Unix domain socket, Confluent will attempt to request the identity of the client from the kernel. UID 0 and the owner of the Confluent process are treated specially and are allowed in without further uh, complications. This allows us to break a lot of the chicken and egg configuration problems where you might not have a client certificate set up, or the network service isn't set up to listen right, or there's firewall rules in effect, and this just allows us to be able to make more of the settings client server at all times rather than having offline configuration and online configuration being distinct access to the same data. So to start with, I'm going to create a root user, which will now enable the jjohnson2 user to log in as root with root's password. However, if I instead create jjohnson2, then jjohnson2 can come in without entering any username or password, since the Unix socket identifies the client as jjohnson2 on our behalf. What we see once we're connected to this interactive client is everything is organized as a file system. Right now there are no nodes, and there are the 2 users that were created in the other session. And in the node groups, there's going to be one node group by default called everything, which by default takes any node. Whether it's indicated explicitly to be in the everything group or not, it will land there in addition to any groups that are also specified. This allows me to do configuration on everything and have it globally apply to all existing and to exist nodes. So right now, if I look at current, there's nothing set except the node membership, which always kind of comes along for free. And I can look at all the available attributes. So what I'm going to do is I'm going to set the current value for these attributes in a global fashion by setting them on the everything group. I'm going to skip console.logging because the default behavior is what I personally desire, and that is to log all the available console data. The console.method I'm going to set to IPMI, and the hardware management.manager is set to the name or address of the node, of the BMC managing the node. In my particular case, we have Lenovo IMMs, and what I'm going to do is specify it by IP address. So I'm saying it on the global level, so I'm going to specify this as a template rather than a specific value. So in my naming scheme, the nodes will have a number, and I'm taking the first number from the node name and I will be filling it into this attribute, and we'll see how that gets expanded in a moment. There are other values available, but I'm going to stick to N0 for the purposes of this video. I'm going to set the password to match what has been already configured on these systems before this demonstration. And the hardware management user is user ID. IPMIKG is an attribute that almost no one will use, but it's available. And so when it responds back, there's a couple of things to notice. One, it detected that hardware management.manager was an expression, and so it does not provide a value. Instead, it just explains the expression, uh, what the expression is that values will be derived from. And this redaction is indicative of some measures that go a little bit deeper than just masking the display of the values. Uh, the API actually does not offer up the read access to the username and password right now. The value is truly, just left blank, and the client's doing the asterisks as a visual indication of what happened. Inside the service, secret attributes are kept encrypted at all times and only decrypted on demand, and then um, the unencrypted copy is removed as soon as it's no longer needed. Um, the decryption key and the integrity key by default is kept alongside the encrypted data, but we are working on uh, functionality to seal that to a password, which would require a password to start, or in addition to the password, seal it to the TPM, which means if a TPM matching was available, it would unseal it by default without a password, or if that TPM is lost, then knowledge of the recovery password would still allow access to the data. So now with the everything attributes defined, I'm going to create some nodes. So I'm going to create N1, N3, and N8. So if I look at N1's attributes, I can see that it got the IPMI console method inherited from everything. The hardware management.manager is 172.30.3.1. Since we're talking about N1, the 1 was extracted and placed here. And it tells me that came from the everything group and what the expression was. And just as before, I'm still not aware of what the username and password is, but I am aware of its relationship to the everything group. So I can then do things like show health hardware, which is a slower operation when it's first done, but a little bit faster on subsequent invocations. The first invocation triggers a download of the sensor descriptions from the service processor, and then reading all the sensors. Subsequent calls reuse the sensor descriptions from the first operation, but then still query all the sensors that system makes available. It also understands a bit more about some of the valid states. So if I go into power and I want to say set state equal to um, bad, it lets me know that the valid options are reset, on, boot, and off. So moving on to the console session, starting the console in N1 drops me at the Linux prompt I had logged in previously. I have the serial console of a system. I'm able to log into its console and as if I were sitting at the local video console. I can also start the console session on, let's say, N3, and we can see what an ESXi console looks like, which is very familiar. It's the same interface that's presented on the VGA console. And I can show what the UE5 setup would look like by looking at N8. And the UE5 setup interface is presented as in the same manner it was on the video console. Returning to N1's console session for a moment. I'll see what happens when I connect via another channel. So right now what we're being told is that the console that we're connected to is called N1, and the last timestamp of data that's shown on screen right now was 1551. What's interesting there is if a kernel panic is the thing you see on screen, you're presented immediately with the time that kernel panic occurred. we also have full timestamps for all the log data at a finer granularity than other console managers do. But you know, but in this particular interface, we just present this timestamp at the very last data. And the other thing that you're going to be informed of is when you start the console session for N1 in another client, you're going to see something indicating up here how many people connected. So when I hit enter, he is immediately apprised that there are now two clients interacting with this console. So when he types, the other user will see it, and also the other client is similarly able to enter data, and both can type and both can see what the other is doing. The next thing I want to show is the web interface, or rather, a demonstration web interface. I have written a demonstration interface with static HTML and JavaScript and CSS content that points to this service with nothing, with XML HTTP requests to fill in the background. The HTML and JavaScript are served up by Apache as just static file content, and there's a reverse proxy configuration to redirect requests to Confluent-API to the Confluent web service. So if I load up my web interface and I go to the URL that my JavaScript and HTML are hosted on, it's going to ask me for username and password, and that username and password, just like from the command line, is linked to PAM in this demonstration. So it fetched a list of nodes and created a row for each node, and then populated it with the power state, which is on, and the health, which for all these three nodes is okay. If one of these nodes was not okay, then a different icon would have been displayed, and the tooltip would have displayed a list of the things that are causing that suboptimal state. One of the assets that we offer up is a JavaScript widget for Serial Console, and I'm going to use that right now to open up N1. And as I'm about to do that, note that I'm going to just disconnect this client. So we have a command line client here that currently reports no additional users. So when I click N1 here, his client count will update, and also a client count will be available in the node I open. So I see that there are two clients available here, and there are two clients connected I can see from here. And as before, these widgets are just like the command line. If I type in the command line, or I run dmessage or whatever, then both web and command line see the data. So both can type, and I can run dmessage, and both will see dmessage content. Just going to control C out of that. And the same goes for any of the other consoles. The N8 still shows the UE5 setup, and N3 shows um, the ESXi console. So all these requests are being pointed at this Confluent API interface. The Confluent API interface, when it observes a browser type access that doesn't have HTTP accept as a background JavaScript request would, it presents a simplified HTML view of available data. So there's the users, the nodes. It's the same data that you saw in the file system. So if I look at power state, just like the command line tells me the valid possible values, it tells me what the valid possible values here is in addition to the current value, which was on. So if I'm interested in the JSON of some data, so let's say I click health hardware, and now I know the type of data, but I want to see specifically what format it would come to me, then I can override the HTTP accept behavior by putting .json at the end and seeing how the JSON would be structured as it was sent down to me. And that applies to anything including like the collections, the nodes collection. There's the N8, N1, N3. It understands and adapts and puts .json at the end. And similarly, you can force .html if you have a browser extension that sets HTTP accept and you really want to see the HTML, then the .html will will present those links in the same manner. And so that is about it for the introduction to Confluent. We have some future plans around enhanced discovery and enhanced boot control, essentially taking over some of the other functionality that XCAT relies on external modules for, as well as some of the functionality that XCAT-D itself implements to help provide some scalability to that instance, as well as provide a facility for other projects to make use of. So with that, thank you for your time.